Okay.
Mind if we record the talk?
All
good? Would you mind if we record the talk?
That's fine, yes.
Okay. Hello, everyone. Welcome to the Maths&Stats seminar. So today we are proud to invite Ralf to give us some talk. Give us a talk on the bicategory and the structure to use bicategory to do some algebraic structure.
Thanks for the invitation. So I'm actually here in Western Sydney University for roughly a month. So there's some time to discuss various things if you want to know more about what I'm speaking about today. And I would like to give you a kind of introduction to why bicategories might be a useful tool to construct interesting algebraic objects. So we would like to start with some simple combinatorial stuff. And for instance, it could be a directed graph. For instance, a simple one, a nice one would be just one vertex, two edges on this. And from this, well, those people who do Leavitt path algebras might know that from a directed graph, you might construct this very interesting Leavitt algebra. So from the simple combinatorial stuff, you might want to construct some interesting algebra. Or rings, if you prefer. You can do it over any ground field or over the integers and get a ring. So, for instance, or algebras. Suppose the Leavitt algebras are typically algebras. So you have a ground field and you have your graph E. And then you make this Leavitt algebra of this graph. And I want to explain how bicategory can help you to go from here to there. And I guess you don't know what bicategories are, or who knows it? Okay, very few know anything about it. That's not bad. So I have to explain what they are anyway. And so then I will give you some examples how this machinery works. So you all probably know one bicategory, namely you all know categories, I hope. Who knows what a category is? You don't. Okay. So a category could be something like, for instance, vector spaces over some ground field. So you have objects, which are the vector spaces, and you have arrows between them, which are the linear maps. That's a category. And categories are the domains of functors. So like you have functions or maps between sets. On categories, you have functors as the kind of natural ways to map one category to another category. They map objects to objects, arrows to arrows, and preserving the structure that you have, like composition of arrows, which you have to have in a category. And if you have learned category theory a bit more than just the definition, you probably know that between functors, you also have natural transformations. And the natural transformations are actually the main point of category theory. That's why they were introduced in the beginning. You want to make precise what it means to have a natural map between two things. I suppose you all probably know tensor for the vector spaces, since we have an example, vector spaces. So if you have vector spaces and tensor them together, maybe you know that this tensor product is associative. So if you have two vector spaces, X, well, if you put parentheses like this, or the other way around, it doesn't make a difference. These are kind of isomorphic in a very natural way. And this is an example of a natural transformation. Now, at least as vector space is finite dimensional, maybe you know that, well, picking a basis in the vector space V, you can then take a dual basis and get a basis for the dual vector space, and there's the same dimension, so they are isomorphic. This is only if V is finite dimensional. And this is not natural, so you have to pick a basis to do this isomorphism, and there is no way to choose this isomorphism which would be a natural transformation in this sense. And so this is maybe the reason why certain things work very smoothly with these kinds of isomorphisms, but not with these kinds. And since this isn't really about categories, I think I won't give you more motivation why it's important to look at this level of structure. But well, you can trust me that this is a very established setting to study mathematical objects. And it's quite important to have all these layers of structure. And this is an example of a bicategory, even a very nice one because it's a strict bicategory. I will explain what strict means in a moment. So this here is, let's say, a strict bicategory. So in a bicategory, you have three layers of structure. You have some objects, you have arrows between the objects, and then you have another layer of arrows between arrows, like the natural transformations between functors. Okay. The kinds of bicategories that I like to work with would be those where rings or K-algebras are the objects. So let's try to set something like this up. So you have here, who prefers rings? Who prefers K-algebras? Doesn't matter. Let's take K-algebras. Suppose Leavitt algebras are a kind of algebras by name, and therefore maybe you want to work over a ground field. You don't have to, but so you want to have a ring where your objects are K-algebras. Want to have a bicategory where the objects are K-algebras. And so what should the arrows be? And here's now, there's probably, well, you have to have a good idea what you want to think about. And from a certain perspective, the thing you care about for an algebra is its representations, or in other words, its module category. So an algebra is just a way of talking about modules and their representations. There are certain algebras where this is quite obvious. For instance, if you think about the group algebra of a group, it's just made to turn representations of a group into modules over this group algebra. And that's why it's interesting, that's why it's studied. So you might think that the important thing about an algebra is its category of modules. So you might say, let's just take functors between the module categories. So you have your two algebras A and B, and you want to map A modules to B modules. And then, of course, you want natural transformations as your two arrows. That's pretty clear. But then if you think a bit more, you don't want all functors, because on these module categories, you have lots of structure. You can add modules and all these kinds of things. And you probably want functors which preserve some of this structure. And a good choice here would be co-limit preserving, if you know what that means. If you don't know what it means, and those who don't know categories probably can't know this, so it's preserving a lot of structure in these module categories. And there's an important theorem describing how those functors look like. So there is the so-called Eilenberg-Watts theorem. Which says that these co-limit preserving functors are all naturally isomorphic, meaning by some natural transformation they are isomorphic to a functor which takes a bimodule tensor product. So there will be a bimodule. I think I want left module, so then this should be a BA module. And you can tensor over A with some other module. So a bimodule means that you have a K vector space on which B is acting on the left, A on the right. And then you tensor this as a vector space, and then you divide out some more relations about A. So this is just defined. So this blank here, where we write some X, and we just send X to this thing, and X is an A module. So I'm taking here M tensor X as a K vector space, and I'm dividing out the relation that MA tensor X should be equivalent to M tensor AX. So this is the way how I can make an interesting construction of a B module from an A module. There's a canonical B module structure on this thing by multiplying the left with things in B. On the M side here, this just pulls down to this quotient. So this becomes a B model in a very obvious way. And this is a typical example of a functor that preserves colimits. And in fact, they're all like this. That's the theorem. So once you know this, you know these kinds of functors. And so these are the interesting functors between these K algebras. If you now do this, you notice one kind of annoying thing, namely, when you do these tensor products, you run into this kind of isomorphisms. So if you, even for vector spaces without any of this complicated quotienting, you already have a problem that tensoring bimodules is only associative up to these natural isomorphisms. So if you compose functors, this does correspond to the bimodule tensor product. If you have this bimodule and another one over B and C, then you can kind of compose them by taking this balanced tensor product over B and giving it the canonical CA bimodule structure. And this does correspond to the composition of functors, but only up to natural isomorphism. So the composition here is only associative up to these kinds of canonical isomorphisms. Similarly, when you have identity functors, they preserve everything, of course, so they must be like this. And you quickly realize that identity corresponds to A itself as a bimodule over itself. So, and if you do this composition with identity, nothing changes. And also here, there's a corresponding isomorphism. If you do E tensored over B with M, that's just isomorphic to M, and also M tensor over A with A. So all this works out fine. So this B as a B bimodule in the obvious way acts as a unit arrow on B. But composition with unit only works really nicely up to these canonical isomorphisms. So when you define a bicategory, then there is some extra structure saying that certain natural transformations which you need to talk about composition of arrows being associative and unital, that should satisfy some coherence condition when you have more compositions. I won't talk about these things, it's just a bit technical. So a bicategory has this kind of structure. You have objects, arrows, and two arrows. You have a composition of arrows, which is, actually it's a bifunctor. So I didn't talk about what natural transformations become here on the bimodule. They're just bimodule maps, of course. So a natural transformation between these kinds of functors is just the same as a bimodule map on these bimodules. So the composition is functorial. If you have maps on here and here, then you get an induced map on the tensor product, of course. And then you have these natural isomorphisms for unit arrows and for associativity, and that's the structure, and then there are some conditions on that. So it's a somewhat tedious exercise to write down all this structure, but in this particular case, it's nothing really bad happening. It's just obvious things that you would be doing anyway if you are studying rings and these bimodule constructions. And this would be a very natural thing to do if you would think of an algebra as a tool to encode some module category. For instance, if you know what Morita equivalence is, this is a notion of equivalence for algebras or rings, which is just saying that these module categories should be naturally equivalent categories. And so this is just the kind of equivalence in this bicategory, which would be the same as equivalence of categories here. Okay, so now we have learned what bicategories are, at least a bit. We would like to use them, of course, for doing interesting things with them eventually. And I think I need a clock. I still am good in time, I guess. So maybe let's start with something simpler. I suppose probably you all know group actions on algebras or rings. And maybe some of you would also know that you can make, in this case, some kind of cross product of the group action, or maybe is it also called smash product? I'm not quite sure. Maybe it's more like cross product or so there's some kind of twisted group algebra. I've also heard that name. So the C star, like we call it cross product. So if you have a group acting on an algebra, you can make a new algebra that encodes the group and its action on your algebra. And you want to understand that construction using bicategories. But first, let's think about the orbit space of a group action and how it could be defined in category theory. So let's look at a group action G acting on a set X. And this is a particular kind of diagram in the category of sets. So this is the same as a functor from the group viewed as a category to the category of sets. And if you have such a diagram, so a functor from a small category into some other category, you can think about what could be its limit or its co-limit. And this has a certain universal property, which I will now write down for you. And I think I might want the co-limit here. Okay, so the co-limit, I give it a name and I call it C. So there should be a map from X to C. We'll call this F. And maybe I call the action here plus phi G. So for every element in the group G, I have some automorphism phi G on my set X. So C comes with a map F. And the property is that it equalizes the group action. So I want that F composed with phi G is just F for all G in the group. So this is the definition of what a co-limit would be for this kind of diagram. If you know co-limits, you probably can check this in a few seconds. And if you know anything about group actions, you probably know what C should be. Can you guess a set C which would have this property that kind of equalizes the group action? How could you use a group action to make a new set?
Subset that is kept by G.
You talk about the invariant subset. That's also nice, but that's the limit, not the code. It's the other direction because it's a subset. This here is more like you have a map from X to it. It's more like a quotient set. So it must be the other interesting construction. And someone in the chat knows, and I don't follow the chat normally, but there's some answers which are actually correct. And X mod G is the right answer. So if you take the orbit space, or I think orbit set is more correct, if you take a set, not a topological space, set of orbits that would have exactly this property. And so the orbit set of a group action is an example of a co-limit. Okay, this wasn't very exciting, but it gives you something interesting for group actions. And it gives you a smaller set. This is because you want that in C, certain things must become equal. Okay. Now, in certain bicategories, you can do something else instead. And that's the interesting way how bicategories allow you to get interesting algebraic objects out of simple data. I want to first explain this for group actions on algebras now to make things, well, something concrete, which you probably have seen before. And then we can later turn to these more exotic things like these Leavitt class algebras of graphs and so on. So let's first talk about some philosophical point. So when you make co-limits in a category, then in some sense you impose extra relations. So you want that in C, certain maps become equal, so certain elements in the set must be equal, roughly speaking. So you make things smaller by imposing relations, which is what the orbit space is doing. Now, in a bicategory, things are a bit different. You get these relations because you want certain arrows to be equal. But in a bicategory, it's not reasonable to ask arrows to be equal. Instead, you ask that they are only isomorphic by a 2-arrow. So it's like when you talk about functors between categories, saying that two functors are actually equal. It can happen, but normally functors are only naturally isomorphic, but not equal. There will be some natural isomorphism between these functors, like in these tensor products. And so these natural isomorphisms actually give you more data and not more relations. So they might make things bigger and not smaller. And ultimately that's the reason why limits in bicategories are more interesting and can give you very complicated stuff starting from small stuff, which is different from here where you get small stuff from complicated things. So it's also nice to make things small and get maybe some good overview of what's happening by making a small invariant from something complicated. But with bicategories, you can do something opposite and start with simple-minded stuff and make something complicated out of that. And I think I said all that on record, so I have to write it down maybe. So I can just continue now. And now let's turn to a group action on a K-algebra. So, of course, at first you might just say, let's take your algebra A, and then you have these automorphisms alpha G for all group elements. And then you want to have some conditions like alpha G, alpha H is alpha GH for all G and H in the group. That's how you would normally define a group action in algebra, of course. But we just learned about this bicategory of bimodules. And in that setting, you could do something else. So you might instead say, so bimodules now, of course, always over the same ring. So you have your basic ring A, and so you have now AA bimodules AG. And instead of this equality, you now say that AG tensor over A with AH. This should be isomorphic with AGH. And in this bicategorical business, always these isomorphisms become part of the data. So this map, maybe I call it mu GH like multiplication. This isomorphism is actually a part of the data now. And typically there is now extra coherence conditions, which you don't need here because these mu GH should satisfy some properties. And so the condition that you want here, in which bicategory theory somehow predicts, is the following. When you're composing 3 arrows, so you have now 3 group elements, G, H, and K. Well, I don't write these parentheses because they don't totally matter. There's 2 ways to simplify this to A of G, H, K. So you can imagine how it goes. You can multiply the first things first and then everything together. You can multiply the second things first and then everything together. And you want that these are the same map of bimodules. There's some more stuff because you also had a condition which I didn't write down, but I should have done it, which is that alpha of 1 is the identity on A. If I say automorphism, it comes for free. It's the only one where this condition actually holds. But if I said endomorphisms, and I didn't say anything about this being invertible here, so I didn't really say automorphism yet, I should add this condition. And so this would just say that A of the unit element is 1, so it's just A. And then there's also a bit more like when I multiply A1 tensor AG, AG. So this isomorphism U1G and so on, they are kind of the obvious maps. And so this is the obvious map. So there's a few more conditions about the unit element doing what it should do in these diagrams that I won't write down here. If you think a bit about all this, you realize that this is the same as a strong grading, or the same as a strongly graded ring. So you could take the direct sum of all these AGs and these multiplication maps, which are now extra data replacing this equality. They give you multiplication on this direct sum ring, which makes this into a graded ring. The associativity is just encoded by this extra condition. And well, this fact that A1 is just the same as or isomorphic to A or something like this here tells you that actually knowing the algebra A on top of this isn't necessary, it's just a part of it. So everything is encoded by this graded ring. And strongly graded just means that these maps are isomorphisms. That's the definition of a strong grading. So kind of by definition, this is what a homomorphism from a group to this bicategory of K algebras and bimodules and bimodal maps gives you. It's the same as a strongly graded ring. Okay, now let's wonder what could be some kind of limit object for this strongly graded ring. Well, first, no, before I do that, I should probably talk about how automorphisms give you this stuff. So if you start with an honest group action by automorphisms, this looks quite different, right? So how do you turn automorphisms into these bimodules? So if you start with the alpha G's, those I want. So I want to define a bimodule over my ring A. And as a set, it is just A, or the vector space, but the multiplication is changed a bit. And what I want is that the left multiplication is just the usual one, but on the right, I'm using my automorphism alpha G to change the module structure. And then this map mu GH well, it has to be this kind of balanced tensor product compatible map. And you figure out that actually there isn't any choice there anymore. It has to be, or, well, there is a choice, but the only natural formula would be something like this. So you should use the canonical right action of A2 on this A1 in this bimodule here, which is given by this formula. And so what you realize is that this is indeed one of these strongly graded rings. And more precisely, in this case, the strongly graded ring that you get, so this thing here, this is this kind of cross-product ring for the group action. So this is how this is defined. So if you didn't know how to define the cross-product for a group action on a ring, it's just like this. So this is just take a direct sum of copies of A over the group. And then on this thing, you define a multiplication by saying that if you have an A sitting at G, this is one notation for an element A in the G summand. And when you multiply it with an element B at H, then you should take A alpha G of B, and then this should sit at the summand GH. So if you turn automorphism into this kind of bimodule picture in the way it should be done, then the cross product now becomes this strongly graded ring that describes, encodes your diagram. So you get something pretty nice out of this description of the diagrams immediately. Now I have to wipe the board again. Okay, now let's take something like a limit or co-limit of this diagram. So remember I had this A, and I had all these bimodules AGs, which I now think of as being arrows from A to itself. And I also had these composition maps AG composed with AH is isomorphic to AGH using these mu GHs. There is one confusing thing in the direction of arrows. Here, to be consistent with the usual bicategory conventions, this only makes sense if this is the composition of AG after AH. So that's how you compose arrows usually. So you write the thing that comes first is the thing that comes after the second map. You probably also teach this to your students and they're confused by this at some point. So this means AG after AH. And this is only possible if you view a bimodule like AB. This must be an arrow from B to A. So that this tensoring is just the usual, is the composition in the same, not the reversed order. This is a bit confusing, but that's how it has to be done so that you don't get confusing things happening here. For that reason, I think I want to limit, not to co-limit, because I have changed around arrows in some way. So let's now talk about the bicategorical limit. So what does a bicategorical limit do? Categorical. Let's call it L. So what we want is that for any K algebra D or something, an LD bimodule, so an arrow from L, from D to L, that's how it goes. So an arrow from D to L, that should be the same, or not quite the same, but equivalent in some sense. And probably we won't talk about this very precisely. So to give you a warning maybe, so these bimodules are only the objects of a certain category of arrows. There's also bimodule maps. So I'm really talking about some kind of difference of categories here. These bimodules would be equivalent to another category. And I only talk about the objects because that's already complicated enough. But everything works out if we do it more precisely. That should be equivalent to, well, let's say cone over the diagram. And now I have to define what these cones are. So cones are how we define limits or colimits and categories. And let's write it down in terms of diagram pictures. So in a cone, you should have an arrow from D to A. So this is actually a bimodule, which has A on the left and D on the right. And then this cone should equalize this action. So if I'm going from A to A using this bimodule AG, then if I go this long way using first M and then AG, that should be the same thing as directly going with M. Well, it shouldn't be the same, it should only be isomorphic. So there should be a 2 arrow here. That is a bimodule isomorphism, which needs some name, maybe FG. So FG will be a bimodule isomorphism, AG tensor over A is M on to M. Okay, and that's exactly the data, but then there is some more conditions. Which this always happens to translate things to bicategories. You get into some extra conditions. And these extra conditions in this particular case would say the following. When you go with M, and then you go with AG, and then you take another element, AH. Well, you can simplify this in 2 different ways. You could first kind of compose M with AG, and then you compose AH with M. So this gives you one identification with just doing M. Or you could do it by first multiplying AH and AG together, and then the other way. So maybe this is AH after AG. So we can go to AHG tensor M to M, or you can go to AH tensor M. This. So this here was something like identity tensor FG, and this is FH. This is FHG, and this is UHG tensor identity. And this diagram of bimodal maps should commute. And then there's also something about the unit element. Remember, A1 is just A, and so this F1 should be just an entity, kind of canonical map. Okay, so the limit L should be a K algebra so that these kinds of FGs with these conditions are equivalent to a left L module structure. Now, if you think a bit about this, the map FG here is equivalent, or kind of corresponds to a map, we call it FG hat, which sends AG to an endomorphism of N as a D module. Namely, FG hat of A applied to M is the same as FG of A tensor M. So this is kind of a standard recipe in algebra and other areas that you just turn a map of 2 variables into, well, a map into maps like this. And you can go back and forth between this map FG and FG hat. So instead of mapping the tensor product here to M, you can just map H into the endomorphisms of M. And if you do that, then you see altogether that so this cone structure is the same as a homomorphism from this direct sum of the AGs into the endomorphisms of M as a D module. We just take, well, the direct sum of these FGs, FG hats. So you can translate this family of maps FG into a single homomorphism on this direct sum of AGs, this algebra. And well, this in turn is the same as a bimodule structure over this direct sum and D. So you see that L could be taken to be this direct sum. So the direct sum of these AGs has exactly the property of the limit. And so indeed, there's a little bit of more work to be done because limits really are just talking about equivalence of categories and talking about objects. So you must check something about this being compatible with bimodule maps and in some sense natural. But if you do all this carefully, you will find out that indeed this strongly graded ring that is attached to this group action has exactly the right property that characterizes the limit of the diagram. Or if you start with a group action by automorphisms, then somehow this bicategorical limit construction doesn't make the algebra smaller, it expands it to this cross product ring which we have made here. So the cross product has now, or let's say the universal property that characterizes the cross product has now been reinterpreted as that of a limit in this bicategory. And so you make your original data bigger because in a bicategory, you have this extra data, these arrows FG, which mean that the universal object now has a more complicated structure than the data you started with, as opposed to the orbit space or the invariant subset of a group action, which has less structure and, is smaller than the thing you started with. Okay, I think I still have a few minutes, and I can now turn to the less easy cases. So here, it wasn't difficult to find the limit. It was just something very natural anyway, and in some sense, it was just reinterpreting the universal property of the usual cross product in a different way. But this was also a very special kind of diagram. What happens if you take a more complicated diagram? Or maybe not a group, but a monoid? What's the simplest kind of monoid you can imagine? Any idea what the simplest monoid is? Natural numbers. That's a good idea, yes. It's not the smallest one, certainly, but it's the free one. It has one generator and no relations. And that's why I think it's the simplest one that's not just zero. I mean, zero is maybe not even simpler, but it's too boring. We don't talk about that today. Let's take the natural numbers. And in that case, natural numbers, what would the diagram be? In a category, it's just one object and one arrow on it from the object to itself. And the same thing happens also in bicategories. There's a little bit to prove there. So you have to prove that all this data of a homomorphism still comes for free if you have this kind of free category. So the free category also is in some sense a free bicategory. But that is true. So a homomorphism from the natural numbers to this kind of bicategory of rings. Bimodules is the same, or it's not the same, but it's equivalent in a certain sense to having a ring. I thought K algebras, right? So let's take here again algebras over K. So you have one K algebra, A, and the bimodule M. So what should the limit of this gadget now be? And once again, you can look at the cone with a given summit. So you fix some other K algebra D. And then a cone would have the following data. You must have a map from this summit to your K algebra A. And then, there's only one arrow here. So there's only one object, this A. So there's only one arrow like this. Maybe I'll call this thing now bimodules X. And once again, for the cone, you want that if you have here X twice this diagram should commute, but it should commute only up to a 2 arrow. So you have an isomorphism of bimodules, M tensor over A with D, tensor over A with X, isomorphic to X as a D module. Actually, this is as A D bimodules. Okay, so that's the data of a cone. So you must have X is an AD bimodule. And this F is such an AD bimodule map. As before, you can do this trick of writing F as a function, as a map from M to endomorphisms of X. So you can translate this to a map from A to endomorphisms of X and a map from M to endomorphisms of X. And this may be F3. So you have X, which has this structure, a map from A and a map from M. And this is in some sense an A bimodule map, and this is an algebra homomorphism. If you have this data, you can now wonder what should be the universal such situation, or what should act on the left on this X if you have this. You can get it in 2 steps. So in the first step, you have to make what's called a tensor algebra. If you have this data, you can also take the tensor product of M with itself over A. This also maps into the endomorphisms on X by just taking X tensor Y goes to F hat of X, F hat of Y. And you can do this with many copies of M. So what you really get is the direct sum of these tensor powers. So M tensored over A with itself n times, starting at 0 to infinity. If you have 0 copies, then you have just the algebra A itself. So this is also part of it. And this is now mapping into the endomorphisms of X. This thing is already an algebra called the tensor algebra of M over A, because it's defined using tensor products. So you see that your X will become a module over the tensor algebra in V. However, the tensor algebra is not yet the right answer, because when you try to make a cone where the tensor algebra occurs, so you are now, you would then get a map from M tensor A with the tensor algebra. So you just send M tensor anything to M times omega. The multiplication here is just tensor product, of course. So when you try to make a cone where the summit is this TAM, you should produce a map from A into it, which is obvious because A is a summit. And you should produce this isomorphism here, where X is now your candidate for the limit, the tensor algebra. And there is a canonical map, namely just multiplying things together in the tensor algebra. But this doesn't work because this is not an isomorphism. So what you have to do is now invert this isomorphism. So adjoin an inverse to this map. And if you do that, so if you adjoin the inverse, then you will have got the right answer. And here I just mention the word cone localization. I don't think I have the time to go into more details about all this. So there is a process of adding inverses to such kinds of maps, which is more general than just adding inverses to one element. An element is, of course, a special kind of module map from the ring to itself, just multiply with the element. But you could also take a matrix, for instance. So let's take a 2x2 matrix that induces a map from direct sum of two copies of this to direct sum of two copies, and you can take the inverse of that. And here you have to take this kind of map and draw an inverse. And at least under some assumptions on M, which I won't talk about, you can do this. In particular, M shouldn't be infinitely generated or something, then it's difficult to make an inverse for this. But in nice cases, if M is nice, you can do it. And well, I think I won't talk about this unless you ask me. For certain nice bimodules M, there is a well-defined process of adding an inverse to this kind of map. And once you have done that, you have gotten the right property for the limit. And so that's what the limit construction gives in this case. And finally, suppose I still have a few minutes left to just say that if you start now with some very, very simple kinds of rings and bimodules, you get interesting algebras out of this. So suppose I just let the first line standing. So what's the simplest kind of algebra you can imagine? Maybe the ground ring itself or some of copies of that. Maybe we had this graph with just one. So you could take as your algebra A to be K and M. Well, it could be K itself. Maybe let's take K squared. So that's not to be completely boring. And if you do this construction, this gives the Leavitt algebra. For the number 2, which is also the Leavitt path algebra of this graph I have drawn at the beginning, one vertex, two loops on it. And more generally, you could now take a direct sum of copies of your ground ring as your algebra, some index set, maybe call it E0, and a bimodule over this is just kind of by definition. So you have here two elements of E0, and then you have something like the corresponding image of the projections coming from these elements in your set E0, which are called vertex set. So for each vertex, you have the projection onto that summit. You can multiply with that and pick out then in M a direct summit. And these have a certain dimension, some number A, V, W. And this would now be the adjacency matrix of a directed graph. So a directed graph is just telling you how many edges you have between any two vertices. And this can be taken as your numbers A, V, W. And so in this way, the directed graph translates into such a bimodule. In this example, for instance, you have just one vertex, so A is just K. And you have two edges, which just says that, this multiplicity is 2. And so that's the dimension of the vector space here. So that's why you get this example. And if you take this limit construction, then you get the Leavitt path algebra over this ground field of the graph E. If the graph E is what I call regular, meaning row finite, and these numbers are also always finite. That's row finite and then also not 0. So for each vertex, there should be some incoming edge in my conventions. In this case, the limit is that. And I think I probably should stop at which point? Now or in 2 minutes or now, kind of. I thought that, so probably I won't say more about this now, unless you ask me about it. So in the end, we have learned then that if you start with something pretty simple, like this kind of graph, then this limit construction, starting with very, very simple kinds of bimodules, produces these rather intricate algebraic objects, which is, of course, a nice maybe way to approach these things and could give a good handle on studying them. But I have to finish now, so thanks for your attention.
Any questions for Ralf? Or any questions from online? I have a question. So I noticed that you mentioned lots of things about bimodule. Is there a deep connection between bimodule and bicategory? Or is that only because the examples are bringing some?
This is just one example of a bicategory which I like because it produces algebras. It's not really the only one you could take. So I have also worked in other bicategories. At some point, I will give a talk at Macquarie University. I think it was April 1st. I think there we'll talk about the bicategory of groupoids and groupoid correspondences. So where your objects are no longer algebras, but certain groupoids, let's say nice Ital groupoids, which we know what they are. And then there's also some kind of bimodules there, which are now called groupoid correspondences. There's also a C-star algebraic version of that, where bimodules become something more C-star algebraic called the C-star correspondence. And you could work in many other bicategories. But these are the ones which are most interesting if you want to get, for instance, interesting K algebras, interesting C-star algebras, interesting groupoids.
Thank you. Other question? Oh, good. If there's no more question, let's thank Ralf once again.